Okay. So on the notes, we're going to add just one problem that asks you not just to find the implicit, not to just use implicit differentiation, but to solve for specific things. So the example is, given x squared minus xy plus y squared equals 9. Given x squared minus xy plus y squared equals 9, we're going to do three things. We're going to write the general expression for the slope of the curve. Write the general expression for the slope of the curve. We're going to find the tangent line or lines for the curve when x equals 0. And we're going to find the coordinate of the points where the tangents are vertical. So we have to do these because these are the types of questions that could be on FRQs. I think, like on the FRQ section, I think they're more common for the AB FRQs than they are for the BC FRQs. The way the AP exam works for you guys, because I don't think you guys have ever had a class like this before where it's two AP exams combined into one, is that when you take the BC exam, it is basically half AB questions and half BC questions, and you get an AB score and a BC score, and you earn separate college credit for both at the same time. So when we look at the results of the AP exam, we'll be like, oh, these 3 FRQs were also on the AB exam. And then there were 3 FRQs that only you guys got on the BC exam. And then the AB, people who only take the AB exam, they get 6 FRQs that are just on their exam, if that makes sense. So I think that it is possible, it might be that they typically get an FRQ that's just like this. I've seen bits and pieces of these types of questions on FRQs, but typically not a whole FRQ that deals with this, if that makes sense. But it is enough that it should be on our radar that we might have to do implicit differentiation on an FRQ, enough so that it's reasonable for us to look at many of these to make sure that we are familiar with them, just in case we ever have an FRQ where we would have to do a question like this. So we are going to do not a lot today, more so tomorrow, but we're going to keep coming back to it. You're going to be like, why? Because we could have maybe one part of a question on an FRQ, because these do show up on FRQ questions. Okay, so just a heads up, that's why. All right, write the general expression for the slope of the curve. What should we even think? What should we do? Derivative. When we see that word slope, immediately we should think derivative. And because it's mixed with x and y in the problem, now we're going to go, oh, x and y are mixed together, implicit differentiation. So we're starting to build those associations with words. One association is slope equals derivative. Our new association now is x and y mixed in the problem, implicit differentiation. Okay, so let's go ahead and start doing that. Derivative of x squared is 2x. I'm going to put my minus with my parentheses, and I'm going to think of this as a positive x and a positive y with the product rule. So, how do I do the product rule? First times the derivative of the second, plus the second times the derivative of the first, all right? Plus dy dx equals 0, okay? So 2x minus, this one is almost like a relief to do after those last two that we did from the worksheet. So much easier. Whew. Do you guys want to leave the dy dx on the left side or move it over to the right side? Leave it on the left? Okay. Okay. Before we start dividing, what do we do? Factor out the dy dx? I don't know if the problems are old or recent, but I've seen FRQs, like actual FRQs that have been done in the past, where part A of the problem was show that this is the derivative. So they give you like a problem like this, and then they tell you this is the derivative, and they say like, show me how to get there. And your job is to do the implicit differentiation that shows all the steps to get there. Which I'm like, that's very nice of you. If you want to tell me the answer and all I have to do is like prove it, by all means, give me the answer. I'll do that. Okay, so it says find the tangent line. So we already know that means derivative. We already found it. Find the tangent line for the curve when x equals 0. If we find the tangent line, we need an x coordinate, but what else do we need? A y coordinate. Okay, so if you're going to find the y coordinate, should you use that x coordinate in the derivative, or should you use that x coordinate in the original problem? The original. Okay, so let's go back to the original problem. Let's plug in that x coordinate. So I took my x of 0 and I'm plugging it into the original problem. 0 squared minus 0 times y plus y squared equals 9. So it's just y squared equals 9. And then if I solve, what do I get? I'm trying to think what we just killed. We have to do plus or minus because we are the ones who did the solving. So if they say square root of 9, then it's just 3. But if we are the ones who do the square root, we got to do plus and minus. Okay. So it's y equals 3, y equals negative 3. What did we just kill? It's up there. Square root is a plus and a minus. Figure it out. I'll put it up there. I know I've had it in the past. All right, plus or minus 3. So that means we have two tangent lines. We got 0, 3, we got 0, negative 3. Two tangent lines. Are you finding it, Cooper?
Yeah, I found it.
Okay, I'll look for it. Don't worry, guys, I'll mark the animal you just killed. Okay, don't worry. All right, so we got 0, 3, 0, negative 3. So what we're going to do now is we're going to take those points and we're going to evaluate the derivative for each one of them, and we're going to have two different tangent lines. So there's two, okay? So I've got dy dx, and this is the notation. If you have dy dx and you're evaluating it at an x coordinate and a y coordinate, you say dy dx evaluated at 0, 3. And so we're going to get negative 2 times 0 plus 3, negative 0 plus 2 times 3. And then dy dx evaluated at 0, negative 3. Negative 2 times 0 plus negative 3. Negative 0 plus 2 times negative 3. Yeah. Okay, if you pull out a negative, then you'd have 2x minus y, x minus 2y. If you pull out a negative, you have to pull out a negative from both pieces. You can't just pull out a negative from the first term. So if you pull out the negative from the 2x, you have to pull out a negative from the positive y as well. Uh-huh. Yeah. So the slope for 0, 3 is 1/2. And the slope for 0, negative 3 is 1/2. So they're different points, they're different tangent lines, so there would be two answers regardless, because they are two different points. Yeah. So we have y minus 3 equals 1/2, x minus 0, y plus 3 equals 1/2, x minus 0. And I do like using Desmos for this one. So you can't do this on a test, obviously, but Desmos is really great for understanding these problems as you practice. And I would encourage you as much as you need to make sense of these problems, to get the answer and then graph it to make sure that you kind of understand what's going on. Because if you never graph these and you never understand what's going on, then you don't get that like big picture perspective of like, oh, that makes sense. So let's go ahead and graph this and see what it looks like. So the next one says, find the coordinates of the points where the tangents are vertical. So our slope was a fraction. When the top of the fraction is 0, that means the whole fraction is 0. That's a horizontal tangent. When the bottom of the fraction equals 0, that means the slope is undefined. That means we have a vertical tangent. Okay, so I'm just going to write that down. If we have slope equals 0 over a number, that is horizontal. If we have the slope is number over 0, that is vertical. And in this particular problem, they are asking where we have a vertical tangent, which means that we are going to take the slope that we found in part A, we're going to take the bottom, we're going to set it equal to 0. Sound reasonable? Okay. So take the bottom, which is negative x plus 2y. Set it equal to 0. And you end up getting, I'm going to add the x over to this other side, you get 2y equals x. Okay. Now, it is saying, find the coordinates of the points where the tangents are vertical. When you find the coordinates of the points, are you using the derivative or are you using the original function? The original function. So what we're going to do is we're going to take the original function, we're going to replace every x with the 2y. That way, the entire original function is in terms of one variable, and it's something we can solve. Okay, so the original function said x squared, so I'm going to write 2y squared, minus x times y, so I'm going to write minus 2y times y, plus y squared equals 9. So I've got x squared minus x times y plus y squared equals 9. Yes? So all the videos, if you go on Canvas and you click on modules, the very first link is not an assignment. The very first link has all the links to the class notes and then answer keys that I've actually uploaded. Yeah. Okay, so 2y times itself is what? So we have 4y squared minus 2y squared plus y squared equals 9. The original equation. So anytime we're looking for coordinates, we're not plugging it into the derivative. We're plugging it into the original function itself. In this case, it's technically not a function. It's actually an ellipse, slanty ellipse. That's not the technical term. Oblique ellipse is the technical term. Okay. So 4y squared minus 2y squared plus 1y squared is 3y squared. Okay, so we have 3y squared equals 9. And then what do? Divide by 3. So then we have y squared equals 3. And then what do? Plus or minus. Okay, plus or minus 3 or something else. Okay. Y equals square root 3, y equals negative square root 3. Okay, so then we can go back up here and we can say, all right, x is equivalent to 2 times the y coordinate. So we have 2 points. One has a y coordinate of 3, one has a y coordinate of negative root 3. And then what are the x coordinates that correspond to those y coordinates? So 2 times the square root of 3 and then negative 2 square root 3. Okay. Now we're just gonna verify this on Desmos because we can. So